Hi. Yes, good evening. My name is MJS Raza, PMRF scholar in the Department of Mechanical Engineering uh, in Trichapalli. So, to welcome to the session at the week 9 for the course of Statistics for Biomedical Engineering. And I am MJS Raja, PMRF fellow and PhD scholar at Trichapalli. So, till the last session that we have seen, that can you confirm that my audio and presentation is visible? It's fine, na? Shall I go ahead? Hopefully, it will be fine. So, till the last class, we have seen what are the testing and all that we have seen. Then we went through the logistic regression. So, I'll just give the brief for a few 4 to 5 minutes and all. And what will be the agenda for the today also that we will discuss. So as I told, like we have started from what is the statistic? How come it's going to start? That going to use in the biostatistic of biomedical engineering, and what are the applications? Is there applications we have seen for the drug delivery or any instrument? Their efficiency we have to check it out, and then we have checked with the multiple cases like if for a particular disease, let's say that the fever or malaria, if that for that particular, we made some different types of the drugs, and we have tested on the different populations also how it effective on that particular that the population. So based upon that we have seen all these things. Then after we came across, like when we go into the statistics, so we have to know that what is the need and what is the role of then we have seen like in the statistic that a statistic will not alone comes in the picture. So the for that we have the foundations for the statistic. It's called the probability. So in the probability, we have also different types of probabilities or theories are there. And if you saw the descriptive statistic also there, if we talk about the statistic, we have the two types of statistic is there. First one is the descriptive statistic is there. So in that will we just go with the numbers, will not conclude on anything. So in the descriptive statistic, we have a discussion of mean, that mean, mode, and all. Then to backing and all that we need the foundation of the probability. So in that also we have seen what is the theory behind of that, what is the expected outcome, or maybe that the that the probability and all. Then we check for the expectation, population variance, and all. We have checked it out. After that, we have checked with the universal testing like central limit theorem. Then we define confidence interval. What is the confidence interval? Is something we are going to tell the range of the probability or any of the statistic value will tell. Then we started with the hypothesis. Hypothesis is something that we are going to make assumptions or something we are going to make. So in we have two different types of hypotheses are there. First one we call a null hypothesis. So in this is that status quo. Status quo is something if any two drugs are there, whether that two drugs having differences or not. So we have to first make the assumptions. There is no differences are there and all. So as we are coming close to the end of this subject, so I'm just giving a brief. Like each class I will be giving the brief, like how it went, how it would be useful and all. So we have checked with the hypothesis testing. In the two types of the hypothesis we have. First one is the null hypothesis, that is a status quo, and second one we have the alternative hypothesis. So first one, we are going to make the assumptions when we have any drugs, and also there is a main their effectiveness or there is no much differences is there between the drugs and all. So what will be the alternate one? There is a differences are there. So that's what we have to prove it out. So but we have to tell based on the numbers or a statistic or probability. What is the power? What is the probability that is not going to happen or something that will be there. So then we have checked for the large sample test, and we came across the p-value. P-value is something we call the that the probability of the rejections, rejections and all we'll say. Then we check about a small sample test. That the large sample test is actually stands for when the large sample, when we'll say n is greater than 30. So for that we have applied the central limit theorem. For that we have the assumptions of that should be IID. That's all. Then we came across the small sample test. Let's say for the small sample test we have the t test. For a small sample that are going to less than 30. So we have used the t test. Then we have checked with the what is type 1 error, then the type 2 error. We make the contingency table like what is the actual, what is the predicted. If they are not able to, that was the actual, but we are not able to do so. It's that the missing the chance we told. Then type 2 error, something we are falsely like we are giving up. Then we check about the chi-square distribution. Chi-square distribution we have checked when that distribution is bit of skewed in the positive direction. It not going to be negative. So that we have checked with that also. After that, we came across the like in that t distributions and all. We have checked with the mean. We are talking about the differences of the mean or differences in the like that the mode and all that we are checking out. But sometimes that mean will not give the clear picture, so we have to go to the variances. But the hypothesis will be there is no much difference in the mean population mean and all. But the way of calculation will change. So in the t-test, chi-square test, it was all we're talking about something called that the mean only. But now we came to the hypothesis test using the variance. For that, we were having the what you can say F test, and that is also extended to the ANOVA test and all. Then we have checked for the contingency test also. Then test of the independence also, like we have fit the any that the probability distributions, like we have fit for that what we can say binomial distributions or Poisson's distributions also we have checked with that. Then we have checked with the QQ plot, like probability plot, like it's a called QQ plot. So when we are going to tend toward the normality, it's going to be like make the straight line like this. So that will tell that QQ. After that, we have checked with the two independent population, like first one with the paired one, and then we check with the two independent pair. Then the paired t test we have that we have to check it out. So when we came across, whenever we have only two samples, so we have to go with the chi-square test or t test and all. But when the number of groups is going to become more than two or three, so in that case we have to go with the ANOVA. It's called analysis of the variance. Again, the things will be like analysis. The population mean will be the same or it's going to vary, but the way of calculation is going to be change it out because that for the ANOVA case we have the more than two groups are there. Let's say group one, group two, group three, and if you go with the one, two, two, three, then one, three, what will happen then in that case type one error is going to be increased. So we have to deal with that. So we came across with the uh, ANOVA. Then we have checked with the mean square treatment and mean square error in the ANOVA. After that, we have checked with the what is the that's called linear regression. Then we check the R square statistic also check, and correspondingly we have checked with the. And in the last lecture, we have seen the logistic regression. Logistic regression is nothing; it's a linear and log function. Okay. So in that we have said it's a logit function, it's a log function. Then we have checked with the log likelihood functions also. Log likelihood, it's odd ratio that we are devising and all. Then now in this lecture we were going to do the ANOVA testing using linear regression. I will not go through the much of that the derivations, but I'll say how. So correspondingly, we have some sort of some optimization functions are there, or that optimized parameters are there. So that we'll discuss. And today class will discuss about the some sort of starting of the design of the experiment. Because now till now we have went through the one-way ANOVA. Now we have to go to the two-way ANOVA. So now the interaction effect which comes into the pictures and all, when the number of sample or number of groups is going to increase, so there is chances of that unnecessary error or whatever unwanted that the factor is going to come into the picture. So we have to design the experiment properly or to deal with that sort of problem. We have to design the experiment like in a proper way. So there is a bit of that today we'll discuss about the RCBD. That's we call random and complete block design. And till here we'll discuss and then we'll solve some problem based upon that. So till the last class, any doubt or anything is there that I should clarify now? Can you please tell? Can you please tell like if any doubt then anything is there so we can have short discussion on that and then we can go ahead with that. Then we'll move ahead to technical.
Regarding something gradient you were explaining, so that can you give little explanation?
Yeah, today we'll discuss regarding that what we say that the multi-cross entropy. Then we'll discuss the gradient descent also. Gradient descent. If we talk about what we can say that a change in or slope, we'll say that's called that the gradient. Today we will discuss any other thing.
Regarding, sir, regarding that log it.
Yeah, yeah. So that the logit function is something we called like earlier we were used to discuss y is equal to ax plus b. Okay. So what we were discussing about y is equal to uh, x plus b. If you're going to, because this is a linear function, so there is chances of the error that all will going to increase. But if you talk about that the logistic regression, so in that case, we are discussing about the binary classification, not discussing about the continuous way. So in that case, if we go with the classification and we'll go with the linear one or direct one, so there is chances of the error is going to more or convergence will not happen. So to avoid that convergence or when we are going to divergence more, so we have to stick to the log function. It's just a method. Like let's say y is equal to x plus b. So if it do like ax plus b, if you go with the log of y plus log of x plus log b, so that function will equal to logit function. Like it's just a logarithmic function. There is nothing much of that. The what do you say? More than that, as we have seen in the last class, that the logistic regression is actually deal with the binary problem, not the continuous one. Binary classification, it's actually based upon the probability. So to deal with the probability, we have to use the logarithm function, that the logit function we say. Is it clear?
Yes, sir.
And so if you come to the some sort of what you can say, when we go to some optimization parameter which comes into the picture. So it's a one which is called a cost function. Cost function is something summarize how well the model is going to behave. Or if you change the cost function, that model is going to be changed. Okay. So in the other word, that we are going to use the cost function to measure how close the model predictions are actual output. Cost function is something. Let's say I have a companies are there. Company A. So they have launched a product. So they did some sort of campaigning. If the company that the campaign A, campaign B or C. So if in that if you're going to influence the cost functions or cost like something we'll take like some parameter we are influxing into the a variable, it's going to give how close the model will like how close that our target is going to achieve. It's something we'll say some sort of input we are giving so that our predictions or whatever we want as an output that we need. So based on the cost function is something we'll say in terms of what we can say, it's in the layman language. Like I want to get the better output or better accuracy or better precision. So we are just influxing some sort of cache. Okay. So this is the whole about what we can say cost function. So in the statistic, we'll say a functions that we are going to influx that if that like how close that we can get the results as the actual output and all. Okay. So in the case of what we can say in the linear regression that we are using the mean squared error as a cost function. So our agenda is to reduce the MSE. It's error. We have to reduce. So that we are saying cost function for the case of regression. But if in the case of company for a campaign to get the maximum output or maximum sale and all, so that the cash or the campaigning method, campaigning strategy will become the cost function. Okay, but in the case of that the logistic regression, mean of square difference between the actual product and outcome become the cost functions. Let's say because the in the in the that the linear regression, it's the something we are going to use for the continuous regression. It's something called that one line. Some point is there, how close it's there. So in that case, that error, that point or this point, that should be very less. And in the case of what you can say logistic one, we have to get binary either 0 either 1. So in that case that the difference between the two factor it should be like so that will get tell that the cost function for the case of so at the cost function might we give the non-convex solution containing many local optima. So this is going to local minima, global minima, and all. So it means cost function is going to increase. Then the error is going to reduce. So I think the cost function is going to be clear. It's something will tell how influencing the our output. That will tell cost function. Is it?
Nice.
So now we have the cross entropy loss. Let's say now because in the case of linear regression that we have checked with the MSE. But in the case of what we can say that the logistic regression, we have to deal with the what? Deal with the by classification. That classification can be binary or that the multi-class. So in that case, so it's something will tell it's a probability to get the either 0 or either 1. It's a probability distribution. So to measure the effect or something we can say like to introduce so that we are saying coming across the cross entropy. Cross entropy loss is a measure the difference between the two probability distributions. First one is the true distributions, but the based upon the data or the predicted distributions we have. Okay, so that cross entropy should be what you can say minimum actually. So we should be deal about. So why we are like let's say so what is the motivation that why should we not do what do you say linear regression, cross entropy and all? Why? Or either we can say why in the classification why can't we use the that the mean square error because it's a mean square error that we are going to calculate for the continuous function. It's that going to use for the linear regression. And actually it works well with MSE that the mean square error. If we take logistic regression, if we take the logistic regression, in that case, what will happen? If we take the MSE, that we can calculate no issue. But the problem is that it's not going to converge, or they will not going to able to classify that our predictions in a proper way because it's going to poor probability contribution. Actually, that the mean square error is not the probability; it's a error. It's just something that difference we have. But the classification actually deal with the probability. So that's why it's we have to go with the something called probability distribution. So that's what the terms came in the cross entropy. So what is the definition of the entropy actually? Can you tell entropy? Measure the uncertainty in the distributions. Is it? Entropic terms itself called measure of the uncertainty in any distribution. So in classification that we are going to quantify how well the predicted probability match the actual class level. So it's right for the information theory. So based upon the whatever information we have, so it's going to be like how can we classify or what is the probability getting a chance like how well we can quantify and all. So where cross entropy represent the expected number of the bits needed to encode the data. It's something that the bits, it's something we call information. So that we are going to use one distribution using the another one. So the closer the predicted probability is to the true level or the lower the loss. Whenever we are going to closer to the whatever, let's say I was expecting that our value will come one. So in that case, the loss will be less because the loss or the error we have to minimize it. If the model is confident and correct, so loss is going to be near to zero, and it is confident and wrong, so that the loss will become high. So that the we are the confidence, but the wrong. What happened? It's the case of overfitting. It's exaggerated or the loss became too high, so that not able to converge. But some values we came across. Okay. So in the regression, we minimize the mean square error. It's a bit of theory. But I'll try to explain that how come it's going to be. And in classification, MSC that not work well because the probability are involved. Whenever in classification is I told you like it's a classification problem that's either zero or one. It's something that probability. So in that case, MSC is actually a error that will not work. So that's why to avoid that we are going to use the log loss function. So that's what I told. If it is simple linear one, so that's what we call log it function to measure how well predicted meant the true class level. So cross entropy comes from the information theory. It measures that the distance between the true distribution and the predicted distribution. So if you talk about the entropy, HP will be minus of summation of I is equal to 1 to Pi log of Pi. It's something that P is the probability. Okay. And if you talk about the cross entropy, so now H, P, and Q. So one is the true level, Q is the something like we have the alternate one. H, P, Q minus of I to K, Pi log of 1 minus P. So this is all about the what you can say that the cross entropy will say. So cross entropy, if you see for the binary classification, cross entropy, if you see, so we'll say L of y of p. It's a minus of summation of y log p plus 1 minus y. It's something that y is the probability. And then log of 1 minus p. So y will be the like something we'll call. And if we talk about the multiclass, L of yp summation of k is equal to 1 to k yk log of pk. It's a multiclass. So it's a similar way what we were having the log likelihood function. Is it? If we remember the last class, we'll see some small problem based upon this also. So log likelihood function LB of beta we were having. It was summation of 1 to k 1 yi log pi plus 1 minus log of 1 minus p. It's a similar of that what we can say that the log likelihood function. It's a something we will say Both are similar only. The only thing that we have to deal with the in a different way. So if you see, if you're going to comparison between the cross entropy to the MSE loss, how come it going to affect? We can see in the cross entropy they have the sharp, but the MSE it's not giving the something called MSE treats the error equally. MSE equally. Okay, and if you talk about the MS cross entropy actually, try to focus on. And if you talk about this is actually a what you can say uh, log function. This also log function. This is not a log function. It's a error. It's a MSC or error is there. So if you talk about the neural network problem in the material that the machine learning neural network problem, if we work with MSC, it's going to give the poor classification. It's again I told because it's all about when we talk about the classification, it's going to give the very poor results and all. And if you talk the, it's going to give better results. So if you talk about the where the applications for the what you can say cross entropy, it's going to be a logistic regression, binary and multinomial that we have seen also, deep learning problem also, such softmax clear or cross entropy will take, and this we call natural language processing. Okay, so in that text classification, language models and all, computer vision, object recognition, image classification, healthcare will see predict that the disease that the disability. If we talk about the what is the probability, it's a cross entropy will be going to always zero. Why? It's a probability. Entropy will be entropy can't be the negative. It's a non-negative. It should be. It's a convex in the parameter. It's going to convex like something will be going. It's a only one minimum will be there, but maximum can be of anything. And differentiable, great for the gradient descent. Like whenever we have any of the curve, if we draw like the curve, like it's a sigma L upon sigma B naught or sigma L upon sigma beta naught. So what will happen in that case? It will give the good results actually. That the minimum when predicted distribution will become true distributions. I think it's clear, na? Cross entropy is something that
Okay, sir.
yeah. So can we solve some one problem? A model predict the probability of the customer churning. You have the following data. A is given, label, and then corresponding that the some sort of probability. Can we solve? How can we get the results? If we apply cross entropy will become what? 1. As we know the formula, what is the formula actually? Minus of y log p plus 1 minus y log of 1 minus p. Is it? So, what we have, true label is going to minus 1 log of 0.9 plus 1 minus 0 into log of 1 minus p 1 minus 0.2. Similarly for this also. Plus, if you take minus 1 log 0.4 plus 1 minus 0 log 1 minus 0.8. I think it's clear. So that's how we can calculate the, if we solve here, we'll get minus of log 0.91. So it will get log of 0.9 8 minus of log zero point 0.4 plus of log of zero point 0.8. It's will going to cut, and it will come some sort of positive value. So this is the cross entropy value. Shall we go ahead?
Yes, sir.
So now we'll come to the gradient descent. Gradient descent is actually minimizing the cost. How come? Let's say we have the loss function. We'll take a derivation in terms of, let's say, loss function is a function of beta 1, beta no, beta and beta 2. So 0, beta 1. So that term we are going to minimize to the 0. But in the case of the reality, that will not comes into the picture. But it's going to closer to that one because that's the numerical approximation. Okay. So gradient descent is an iterative optimization algorithm which finds the minimum of the differentiable function. It's something we have, or we have the cost function, or that optimization problem, like we have to minimize. So in that case, so in the process, we are going to different value, update them to reach the optimal ones, minimizing the output. It's something minimizing the error. So minimum of j theta. Let's say we can apply this method to the cost function. In the case of that logistic regression, we have the cross entropy. It should be very less. So now we can find the optimal solution, minimizing the cost over the model parameter. It's a something minimization of the j theta. It's something gradient is something we call slope, finding out the parameter using the slope. Is it? And the idea is to move in opposite direction of the gradient to reduce the loss. Okay. So how we're going to calculate? That we're going to calculate like some theta new will be theta old minus that eta, that's the learning rate, and L of theta. What is the N or eta is a learning rate. Learning rate is also, it's going to define like how come that we're going to make our convergence fast or slow. Okay, so that the learning rate is something they're going to learn from the past. Okay, and theta L, it's a gradient of loss with respect to. Okay, so if you talk about the linear probability model and logistic regression that the model, we can see how come it's going to make some differences. This is the log function. This is going to give linear probability model. So what happens? So in the case of logistic, they're going to give more picture of the slope. Okay, with that the with respect to the that the linear probability model. Okay, so now we'll see what is actually whenever we have the it's like imagine if we are going to hilly train, the cost is the surface. Gradient descent will tell which direction to walk. It's a steepest descent on and how big a step to take to reach the lowest point. So it's a how step that learning rate that we call eta, and which direction to walk. Steps descent is something we call that L of theta. Okay, so in that statistical model, it's going to involve between the beta and theta on weight. If it told about the artificial neural network will be having some weight will be there. Input and output will give some weight, and it will come input some weight functions, then it will come the output in terms of classification. So if that we have to deal with the weight also. So that the goal is to find parameter with value, minimize the loss function. So gradient descent actually is a to find out the find out the parameter with keeping the mind like we have to minimize the loss function. That the loss function can be MSE for the linear regression, or for that the cross entropy for the logistic regression. This one for LR, or no, linear, and this one for logistic. Exact solution possible in the case of linear regression. But in logistic regression or deep learning, that will tell iterative optimization. Instead of going directly exact solution, in the case of linear regression, we can get the exact solution. It's a normal equation. We can get if this that the single equation comes into the picture that we can play about. But if we talk about the classification or in the logistic regression, we have to go with the iterative solution, or we'll get numerical approximation instead of getting the exact solution. Okay. So if we talk about mathematical concept for the linear regression, that the loss function what we have, loss function we have L of beta into beta 1, that what we call slope and the intercept is equal to 1 by n summation of 1 to n yi minus beta naught plus beta x. This is the loss function. So the gradient will become delta L upon delta beta and delta L upon delta beta 1. So this is become the gradient. Is it? It's clear?
Yes, sir.
So now we'll go to the, we can see that how it's a blue curve which shows the convex that the loss function, it's a beta square, and that we can see here. It's a loss function and descent path. So that error they're going to minimize and all. So we'll go ahead with the learning rate. I told you like how they're going to tell like how big a step or how slow we have to take it and all, so that its learning rate is a step function. Let's say I am running a problem. I have a 10 meters is there. Now I can go with the, we'll take a 5 meter one step, or if we want to get, if we're going to discretize in the some n number of problem, like it's a small number, we can get the each and every detail that step size. But if we're going to increase the that the step size, what will happen? It's going to overshoot or it's going to diverge. In the case of that the machine learning problem. So that's why to get the problem at or the that the parameter or what we can say characteristic for the whole length, we have to that the learning rate should be or step size should be very small. So what will happen? It will become that they're going to increase the computational cost. It will become the problem slow. But the thing is that we'll get better convergence and all will get. So that the learning rate actually control the step size. Okay, let's say I have a run we have the EMU signals are there. EMU signals are there. That is going to be like we applied some force and we got the amplitude. This is the time we applied the force. At this point, F become maximum. What happen if we get if we take two step size from here to here? So it becomes the step size that's bigger. But I want what's happening between the here to here. So we have to reduce the what we can say step size. It's called going to be learning rate. We have to reduce it. So means too small. We have to crawl slowly. Means if we take this much, again this much, again this much. If we take, we have to from one step to second step. So this is how the learning rate play into the picture, comes into the picture. Okay. So what are the types of the gradient the descent we have? First one is the batch gradient descent. Used entire data set each update. We'll take one batch. That we're going to take the slope of that. It means stable but slow for the large data. Then we have the stochastic gradient descent. It's a for the one sample at a time. Let's say in the batch we can have 100 number of samples are there. We'll take at a time. So that will become the batch gradient descent. If we talk about the stochastic gradient descent, for each sample we'll go at at it one time. We'll take each sample, so it will become the noisy but fast and work for the big data. Then we have the mini batch gradient descent. Sometimes if we take like each sample at a time, what will happen? So there might be a noise will be there. So they will try to create the problems. So what we'll take similar homogeneous problem. We'll keep in the mini batch. Let's say one batch is there 100. We'll keep 10, 10, 10, 10, 10 batch, and then we are going to apply the gradient function. In that case, it will become the stability and speed will gives the clear picture, stability and speed. So we are going to use the small batches. Okay. So if we talk about the conversation challenges in that local minima, it becomes the not convex problem. Saddle point also that will be there, because saddle point is something that will become the flat or something that will not able to get any the changes in the slope. Then vanishing or exploiting the gradients means it's a deep network. We are not able to get the exact clear of the slope and all. So what will be the solution? We can give the momentum or adaptive learning rate. It's a Adam boost or RMS proportion. We'll give something like from the past or from the it's something we call from the thing we have to learn from the past, and then we can give the adaptive learning that the based upon the error. So they will learn by themselves, and then they will come into the picture, so that they will we can get the better that what we can say that the parameter by minimizing the loss functions. So if we talk about the applications where we can use linear regression for the MSC minimization, logistic regression, cross entropy minimization. I'm saying about the gradient. Okay, so we have to minimize the word MSC. What is the MSC? It's a mean square error. And that the logistic regression, we have the cross entropy minimization. What about the neural that the network? We have the train weight with the SGT. It's something called like saddle gate and all. Then that we can use for the finance, healthcare, NLP, and image recognition. So I think this two optimization parameter is clear, is it?
Yes, sir.
So now we will discuss like we are going to do the one way ANOVA using the linear regression. Then the question will come, then why would we go and all? Because when that the linear regression case is there, we can directly apply. But the thing is that what will, in the ANOVA cases we have to make the groups, that two more than two groups. What will do in the linear regression column one, 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 two, 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 three. This is all are there. So there is chances that they will get the overshoot and all. So what we'll do, we can categorize this similar into the one group, second group, third group, and then we can play about. So that's how we can make the ANOVA problem like bit of more like simple and then clear. So there is some sort of what we can say we have the rules are there. So there is one normal equation for the each parameter in the model estimated. And the similar way, like we have to do that the model will be y is equal to mu plus alpha I and ij, that the mu will become overall mean and alpha will become the group that will going to create some sort of uh, imaginary groups and all, and then eta ij is something called error that should follow the normal distribution. So what is the advantage of the regression? So they're going to unify framework means That the regression and then ANOVA works on the same machinery. Flexibility, we can easily extend to the covariate and then interaction. What about diagnostic? We can get the residual plot, leverage, and then get the influence and all. Okay. So if you see about, so feature will be the group effect, it's a alpha I. Regression will be the dummy variable coefficient. So whenever we have the regression problem, regression problem is there. So 1, 1, 1, 1, 2, but that we don't have any groups. So what we have to do? We have to create a dummy groups so that we can play about the ANOVA. Mean comparison will become what? Group means. That will be the intercept plus contact. Hypothesis test will be F test. That the here also F test. Model fit will be the between within the variance. But here it will going to explain plus residual variance. So what will be the ANOVA logic? Again, I'll take one page actually. That will solve some problems of that. Then we'll get to know that what is the exactly it is. Okay. So that the model we have y is equal to mu plus alpha I and then error. And ANOVA will become SST. How will take it? Then we have the between the group and y cap I y bar square. Then between the group we have ij yij minus y bar square. So all we know that SST is equal to SSB plus SSW. Is it? So what we have to do? Let's say F test will become H naught something will be there. So F will become MSB by MSW. I'll take one more page. Okay. So what we're going to do? We are going to create a for a K group. We use K minus 1 dummy variable. So let's say we have a three groups are there, and so that we can define x1 is equal to 1 if it is belong to group B. Otherwise 0. X2 is equal to 2 if belongs to group C. Otherwise 0. So when in that case that the regression model will become y is equal to beta naught plus b1 x1 plus b2 x2 plus error. So beta naught will become mean of group A. That will become the baseline. Beta 1 will become between the A and B. Beta 2 will become difference of mean between C and A. Okay. So they are the parameter that we are going to use for the what? That we are going to use for the ANOVA. We'll take one more page. That don't worry, I'll take one problem actually and we'll do it. So in that case, F test will become F is equal to SSR full, SSR null, K minus 1 upon SSE of full upon N minus K. I'll show you what is the SSN also. So let's say we have a researcher test the cleaning effectiveness of the three gradient A, B, C, that the whiteness score of the clean clothes are. So they have given detergent. So now we'll score. Then now we'll decide X1. It's a B. And then we'll decide X2 C. First one is the what we have A. What is the score? 77. But it's a baseline. So it will become 0. A. What is the value? 81. 0, 0. We are trying to create a like X1 and X2. A. What we have? 76. 0, 0. Then we have the B. 74. X1 will be the 1. But so B is actually a like it's going to be like A and B, not B and like C. So it does say will come to the 0. That we have defined here. We can see here. X1 will become if group B, otherwise it's a 0. For the group B, it became 1. For the group C, it became 0. What is the B? 66, 1, 0. Again B we have 58. Then what we have? 1, 0. What about C? 73, it's going to be 0, it's going to be 1. C, 78, 0, 1. C, 69, 0, 1. So now we have told like X1 will become 1 if detergent is B, otherwise C. X2 will become 1 if detergent C. So based upon this only we have created this table. Okay. So we'll take some more pages actually. We will go and solve slowly. I think till here it's clear now. So now we have to, what will be the specify regression model. What is that? Yi will become beta naught plus beta 1 x1 beta 2 x2 plus ei. So now we can get the ya. What will be there? 77 plus 81, 76 by 3. What is the value? 74. This is same value. Then we'll get how much? 76, 66, 73.3. Okay. How can we get it? Beta 1 will be, beta 0 will be the YA. If you see here, beta is the mean of group A, YA. So how much it became? 76. Beta 1 is the YB minus YA. How much is that? 66 minus 76 is become minus 10. Beta 2 YC minus YA. I think till here it's clear. Sorry.
Okay, sir. Clear.
Yeah. So we'll get how much the number 73 minus 76 will comes minus 3 point something. 2 point will comes in the picture. 2.26 will comes in the picture. So what will be the regression equation? It will become how much? Y will become beta naught. How much is there? 76 minus 10 x1 minus 2.26. It's a x2. So till here we have calculated what? Till here we calculated the regression equation. So what is the next step? To get the SST. Is it? What is the formula for the SST? It's a summation of yi minus y bar whole square. Is it? So for a case, what is the value we have? 85 minus 80, like what is the value we have? Y bar we have to get. How will come? All summation of all by 3. I'll take the value where I have, I'll that, let me see where is the value actually. But we have the value of the that's the y bar. It will come summation of 77 plus 81 plus 76. No. We have some different values are there. No, that there are similar values are there till 69 by 9. How much it came? 73.33. So for A, in A, how many we have? 77 minus 73.7 plus, is it? But we have the value of another value of, what we have? 81 minus 73.3 whole square plus what we have? 76 minus 33.3. So that is for A. How will get it? How much? For the B, again, what we have the B? 74, 66, 58. 74 minus 73.33 whole square plus and 66 minus 73.33 whole square plus and what we have 58 minus 73.33 whole square. We'll get some value. C. What is the value we have now? What we have? 73 minus 73.33 whole square plus 78 minus whole square, then 69 73.88 whole square. We'll get C. So now we'll get there. SST will become A plus B plus C. Is it? So we'll get some value. I think SST will come total. If you calculate, I have the value 370.89. So now we have calculated the SST. SST we have calculated. So I think in the steps, I think it is clear. Now we'll go with the SSR. We were having SSB. So now we'll, because we are going to the regression, we'll go with the SSR. Okay? SSR now, formula will be there. Summation of yi minus y whole square. How will get it? How will get it? For the group A mean, this is the group A mean, group B mean, minus of overall mean. So for the case of A, it will become how much we have the group mean YA? 76. 76 minus 73.3 whole square. Then what we have? Second group 66. 66 minus 73.3 whole square. What we have next one? 73.33. 73.33 minus 70.33. What will get? That will get SSR value of total of 260.89. So SST we calculated, SSR we calculated. So now we can calculate the SST will become SSE plus SSR, or SSE actually a residual. Similar way we were having a SST is equal to SSB plus SSW. Similar way here also. SST minus SSR will become, it came 110. So now degree of freedom we have to calculate. How much will come? For the case of how many that the group we have? 3. So 3 minus 1, it will become 2. Then what about next? Will become n minus k. Total number was 9 minus group, it becomes 6 for the degree of freedom 2. What about the overall? N minus 1, 9 minus 1, 8. Is it? So F will become MSE. No, MSR by MSE. How will you get the MSR? MSR will get by SSE by degree of freedom. How will you get the degree of freedom? You have the 6. No, that we have 2, that the 2 groups are there. So now we can calculate some value we get. So now based upon the 2 and 6 and 0.05 from the table, then we can calculate. So I think it's a clear now. Everything is same. If you want, I'll take one more problem and then we can solve. Shall I? Hello.
No need, sir. It's clear.
Okay. So that now we are clear with the what we can say, like that the one way ANOVA with the linear regression. Now we'll go to the design of experiment. Can you tell what is the what do you mean by design of experiment actually? What do you mean by design of experiment? Let's say I'm going to collect the some data and all. We have to get the beforehand checklist. Is it? So it's something we are going to design the experiment. Let's say I want to collect the data for a drug efficacy. So we have to find out the what is the population, what is the age, what is size, gender, and all. We have to define it. But there is sometimes the error will come. What sort of error will not able to execute the plan also, or some sort of will not able to what you can say get the data properly also. So in that case, so some sort of something that we have to know what are the unknown factor that will comes into the picture while taking the data and all. For a statistician, we'll be having two types of the things we can do. One, we can design the experiment, or second, we can analyze the experiment. So in the analysis, we'll tell the machine learning people or that the data scientists will do. But for design of experiment, A, that the biomedical engineers and all, for the data scientists, they have the two options are there. Either that the one data will be already collected, that so they are going to analyze the data. But in the case of they can design their own experiment, collect the data, then they will do the experiment. So they will do the some sort of what you can say analysis or testing. It's a inference statistic and all will get it. So but there in the design of experiment that we would take it out input some factor that we can control, some factor we can't control, and we'll get the some output. So in the process, we'll say it's a data processing. All will say. So whenever that we're going to design a simple experiment, we have to check with the are these two solutions only quenching the media of the potential interest. It's something we have taken one example and then based upon that only, or any other controllable factors are there or not, or we have to identify the uncontrollable factors also, then we can get the general output. So what are the objective of the experiment that are going to that determine which variable is going to most influence on the response, and our agenda should be this should be that factor this flow, but not the uncontrollable factor. So first we have to finalize the which variable is going to play most influence on the response of the y. Then determining the where the set of influence of x's and y is the almost near to the desired nominal value. Where that we have to find out the closest value. Then determine where the set of influence of x that the variability in y should be the small. Let's say y that one is the actual one, y predicted. So we have to come up with the x value. In that case, variability or error, it should be small. So that is our objective of the experimental set it should be. Then determine the where set of influence affect the uncontrollable, it's a minimize. I told whenever we are going to design the experiment, our uncontrollable factor should be minimized. Means majority of the factors should be played, or majority of the things that should be played by the controllable factor. Let's say if for a drug we have that we have some sort of something that we are having in control. Second thing will be that is the uncontrollable and all. So that we have to minimize the uncontrollable factors and all. So that is the purpose of a designing the experiments more. So experiment design is a critically important actually for a scientific or engineering world to improve the product realization process. It's something that whatever the efficacy or where how can we implement to the market for the any drugs and all. So in that case, improve the process of the yields means efficiency of the drugs, or if any manufacturing things we are taking, so that things efficiency should increase. Then reduce the variability and closer conformance to the nominal target requirement. So we have to reduce the variability, but it should come closer to the whatever we have the requirement. Reduce the development time, reduce the overall cost. So that is the some sort of general objectives are there. Then what are the principle of the design of experiment we have? So it's a statistical design of experiment. We'll do the uh, randomization. Randomization is something that we are going to will not take a data is in something like let's say 1, 2, 3, 4, 5, 6, 7, 8, or it's like a sequence. We're going to randomize. We'll say 1, 3, 4, or 4, 5, 6, 7, 8, 9, and then we have to do the replications also. It's something to better conformity of the first trial whether it's correct or not. We have to check with the replications also. Then we'll check with the blocking also. Blocking is something we'll take a 1, 1, 2, 1, 1, 3, it's a similar feature, and we'll going to make a batch. Then we'll do the blocking. It means they are going to reduce the factor, or they are going to so they are going to reduce the what do you say degree of freedom. So it's called the blocking. Then it's a factorial principle. Whenever we have a number of variables or more, we have to use the factorial principle. Actually, it comes under the two-way ANOVA that we will discuss that the second or maybe the after first lecture or second lecture we'll see. Like after like coming lecture or after the in the coming lecture we'll see. So in the statistical design that is going to it's going to be necessary. We wish to draw a meaningful conclusion from the data. So anyway, whenever we are going to be a statistic and all, we have to our approach is to we have to take some meaningful conclusion. If that the let's say we have taken some data and we have done the testing and all, we have spent some money or spent some time and all. If something that the positive is not coming into the picture, it means they are going. So we are wasting the resource on it actually. So so that's why it's very important to design the experiment properly. Whatever we have discussed as such, it's a after the design of experiment. So, but we should have the idea like how should we design the experiment so that we can cost we should reduce, time we should reduce and all. So, that's why in any experimental problem we have two aspects. One is the design of experiment. Second one is the statistical analysis of the data. So the both part is very important actually. So means that if the design will be having some flaws, will not able to execute or will not able to get the whatever we need. So in the randomization is the concept underlying the statistical method in the experiment design. We are going to mix it up. Will not take sequence wise. It means allocation of experiment material and order in which the individual runs on the experiment are to be performed are randomly determined. In that case, observation should be independent distributed from the random variable. Whenever we take, it should be a random or independent variable. By replication, we mean an independent repeat run for the factor combination for the confirmation. In the blocking is a design technique used to improve the precision with each comparison with the factor. Blocking is used actually to reduce or eliminate the variability. Let's say for properties A, we have some 10. For properties A, 11. Properties A, 13. Based on this, we can take. So we can block this as, or either A to C, we can make one block 1, or A to D, we can make block 2. No, D to F, we can make block 2. So it's something we are going to reduce the variability and all. Okay. Then, what are the guidelines of the experiment? Recognition of and statement of the problem. Pre-experimental planning and all, you have to do selection of the response variable. So and choice of the factor, label, and ranges. These are the all like before the experiment you have to do. Then after choice of experimental design, either we'll go with the blocking, or either we'll go with the factorial, either we'll go with the replications or the randomizations and we'll go. Then we have to do the perform the experiment. After that, statistical analysis that we have to do that we have to do it's important like for to get the any conclusion we have to do the statistical analysis and all. Then conclusion of the experiment. So now so today agenda is actually we are going to randomize complete block design. Complete. Why we are saying RCBD? It's the name RCBD. It's a complete block design means each block number of sample will be same. Let's say I have some 16 samples are there, and I'm going to that the make of the block 4. So in each block it should be 4. It can't be two block for the block 1 we have the 4, for the block 2 5, but for the block 3 we have the 3. No, we can't. So it means we have to take the complete block design. Like I'll show you here like how it will look like this. Block 1, block 2, block 3. But T1, T2, 3, T4. It's randomized. But the number of sample is the same. Means 4 treatment. But it's randomized. T2, T1, T3, T4. T4 here, T2, T2. Like it's something that we can do it. So in the randomized block design, it's an extension of the pair T test. Nothing. I told you like we had some samples are there, but it's a extension. We have the two groups now. So now it will become 3 block, 4 block, but the number of sample will be same. It's a similar way we are going to use it out and all. Randomization is actually we can Newton's factor is known as a, but in the randomization they're going to play a safeguard against the uncontrollable factor. That we'll see like in the coming part. Then if if we're not going to control, if we not control the uncontrollable factor, inflate the error variance, then we can't make the difference in the treatment. Blocking principle is actually group experimental unit into the block that are relatively homogeneous. Homogeneous means it's a similar properties. Within each block, compare all treatments. Complete all treatments occurs in each block. Let's say because T1, T2, T3, T4 in the case of one block. So in the second block also should be T4, T2, T1, T3. All treatment should come into the second block also. In the third case also, the same treatment should come that the here also. And the randomized treatment are randomly assigned to the unit within the blocks. Like here, T2, T4, T3. It's a similar, it's randomized. So testing like 4 fertilizer on a crop yield, but the that the quality across the plots and all. So treatment will become the factor of interest. It's a fertilizer, drug, and method. Block nuisance source of the variance, soil, subject, and time period. So total number of units will become n is equal to t by p. So what will be the statistical that the model for the RCBD? Y is equal to mu treatment plus block plus error. So that is the T is equal to effect of treatment, B is equal to effect of block J, EI will be the error terms in. So what are the assumptions of the RCBD actually? So it's a similar way what we have for the ANOVA also. Observation within the each block are independent. First one, let's say because here we can see here, it's all are independent of the each other. Error are normally distributed with the mean zero constant variance. Similar properties or similar assumptions what we make. Okay. Then treatments are randomly allocated to the units within the each block. So again, one more. Additive model, no interaction between the block and treatment. Whenever there is an interaction, it will come under the two-way ANOVA, not one-way ANOVA and all. So how can we make the model? Y is equal to mu treatment plus block plus EIJ. So similar to variability, similar to ANOVA, we can do the partitioning of the variance. What is that? Total sum of squares. What is that? SST. Summation of I is equal to 1 to I like T J is equal to 1 to B Yij square minus grand total by N. I'll tell you what is the things and all of the N. GT square. Grand total. I'll tell you what is that. Then treatment sum of a square. In the ANOVA, we were having between and then the within. But now here we have the between the that the treatment between the block. So we'll say SSTR. We'll take T1 square plus T2 square till Tn by block number of block minus GT square by N. We'll solve the problem, we'll see. Then block sum square. SSBL. It's a B1 square, B2 square, B3 square by number of treatment minus GT square by N. So now total we have calculated SSTR, we have calculated SSB, we will calculate. So now we'll calculate the error. Error sum of square. SSE will become total minus SSTR minus SSBR. Is it? So TI is actually a treatment total. BJ is actually a block total. Then we have the GT, grand total. Like summation of T and B. Then what we have N is equal to T into B. How many number of T, like the treatment, how many number of the blocks are there? Okay. So what will be the ANOVA actually? ANOVA table? First one is the source. What will be there? Treatment, block, error, total. What is the degree of freedom? T minus 1, B minus 1. For error, T minus 1 into B minus 1 and TB minus 1. What is the SS? SSTR, SSBL, SSC, SST. What is the MS? SSTR by T minus 1. SSTR by T minus 1. SSBL by B minus 1. SSB minus T minus 1 up into B minus 1. So what will be the FT? F for the treatment. MSTR upon MSE. What about the FB? MSBL by what? MSE. I think it's clear. Whatever the now we have that we have calculated. Now we'll go with the one problem. Is it? Shall we do one problem?
Yes, sir.
Okay. So for the block A, what we have 50, 55, 52, 58. Similarly, we can now we can calculate the grand total. How much it will come? Summation of 50, 55 plus 52 plus 58 plus 48 summation 57. How much it will come? Let's say it's a 629. So first step is to SST. What will be there? Summation of Yij square minus GT square by N. It means you have to calculate 50 square plus 55 square plus 52 square plus 58 square plus 48 square till 57 square minus 629 square by how much we have the n? N 3 and fertilizer 4. So n will become how much? 3 into 4 bar. Is it? So SST some value will come. So now we'll go with the SSTR. What is the formula? T1 square, T2 square. Is it? T3 square, T4 square upon number of B minus GT square by N. Is it? So what is the measurement of A? That the summation 50 plus 48 plus 47. 145. 55, 54, 437, 512, 162. 50, 50, 100, 151. 50, 50, 50, 150, 8, 6, 14, 21, 171. Is it? So SSTR will become 145 square plus 162 square plus 151 square plus 171 square by 3 minus 629 square upon 12 will get some value. We'll take two more page. Okay. So now we calculated like SSTR. Now we have to calculate the SSBL. How will get it? SSBL will come 50, 55, 50, 58. How much it will come? 215. 48, 53, 50 plus 56, 207. What about 47, 54, 49, 57? How much we have? Again 207. So we'll do 207 square, 207 square, 205 by 4 minus 629 square by 12. We'll get some value, SSPL. So what is the SSE? Will be SST minus SSTR minus SSBL. We'll get it. So what will be the degree of freedom? Degree of freedom will be for treatment. How many treatment we have? 4 minus 1, 3. For block, V minus 1, 3 minus 1, 2. Then what we have? Error, T minus 1 into V minus 1. How much it will come? T minus 1, 3 into 2 is 6. What about total? Total will be N minus 1, 12 minus 1, 11. So now we can make the innovative. What is the source? Degree of freedom, summation, MS, F. What is the source we have? Treatment. Degree of freedom, 3. Block. Degree of freedom, 2. Error, 6. What about total? that treatment, how much we have, how much we have SS total. It will come 133.59. SS, no, SSTR is there 130, and SST how much is there? 146.92. Then SSBL how much we have? 10.67. So 133.59, 10.67, 2.66, 146.92. So how much will become MS and all? 133.59 will become 44.53. 10 by 6 by it become 5.34, 2.6.44. Is it? So what will be the F for the treatment? 44.53.44. F block. How much? 5.3.0.44. So now we can get the value for the case of treatment. How much is the degree of freedom will be the 3.6 at 0.05 from table. For the block F2 and 6 at 0.05. So now we can calculate like whether so there is any whether we are going to reject the that null hypothesis or not. So I think it's clear na this question. It's clear na. Shall I go ahead?
Yes, sir. Yes, sir. Proceed.
Okay. So what are the question we have now? We'll solve some problem. So that the so the steps is similar. Calculate the SST. The formula what we have, summation of Yij square minus grand total square by n. Grand total is summation of Yij. Then SSTR. It will be a T1 square plus T2 square, T3 square by block minus GT square by n. SSBL. It's a B1 square, B2 square, B3 square by T minus GT square by n. So then SSE will become SST minus SSTR minus SSBL. After that, we have to calculate the degree of freedom. Degree of freedom is something for treatment will become T minus 1. For the block, it will become B minus 1. Error T minus 1 into B minus 1. Total N minus 1. So here T is the summation of Ti. And here B is the summation of Bi. It's a block one. So after that, based upon that, we can calculate the, what we can say. We can make the ANOVA table. Okay, so this was the overall for RCBT. Okay, so now we have the question in the context of cross entropy loss for binary classification model. If the predictor probability of the class 1 is 0.09, what is the true and the true level is 1, what will be the cross entropy loss? Can you tell what is the formula for the cross entropy for the binary classification? For binary, just tell the answer. I'll wait. Y is equal to minus of,
Minus B and
yeah, yi log of pi 1 minus log of 1 minus b. So they are saying like it's for the 1, class 1 minus 1.9. Then the true label how much? 1 minus 1 log something, some values are there. So 1 minus 1 will become 0. So it will become log of 0.9. So answer will be B. Is it? So anyway, that the entropy can't be the non-negative. Log of 0.09 will become some negative value will come. So this can't be the answer. 1 minus this is simple, exact error, not the logarithmic one. This is again a simple probability. It's not going to be related. Okay. So it's going to be like this. So I think it's fine now. Next question what we have. In the randomized control, in the sort of randomized complete block design, blocking is used to. Actually, what is the purpose of? Tell me. Eliminate the variation due to the known nuisance factor. It means uncontrollable factor. It's a correct one. So blocking, what we are doing, we are trying to reduce or eliminate the variation due to some sort of uncontrollable factor. So that is the correct answer. Let's see the second option. Increase the degree of freedom for the error terms. No, when we are going to make the blocking, what will happen? Eventually, the degree of freedom is going to decrease, not the, is it? It's a part of variations. It's not. So effectively, it's going to decrease the degree of freedom. So this can't be the answer. Ensure that all treatment level are applied equally. This is the part of before, like it's a start, like what you can say, before the experimentation. It's the design of experiment. Is it? Or it's actually assumption. And then the D is that the randomize the assignment of the treatment to the subject. It's again a assumption, not the purpose. I think it's clear. Is it clear? So in the experimental design, actually, that the RCBD actually is used when there are a known source of variability called the blocks that could influence the outcome. Let's say for the testing fertilizer on the crops where soil facilities are varied, field becomes the block. That the soil type, or where we are using that the moisturizer level. So the idea of blocking is to control or eliminate due to the nuisance factor. That our idea is to check the variability for the fertilizer, not the soil type. If it is the soil type will comes, so that we have to do it. But the thing is that our idea is to do the fertilizer, not for the soil type. So that's why we have to eliminate the soil variability. We'll try to minimize. That we're not going to eliminate fully, but we have to do it. So that the treatment effect can be studied more precisely. What will happen if that factor or influence of that soil will come most into the picture? So what will happen? We'll be getting less precise answer for that. So that's the idea. Two, we are going to do the blocking. So in the RCBT is used the block, but the primary role of the blocking is the variance reduction. So that is the idea of to do the what you can say randomized complete block design. Now the third one, that the null hypothesis in one way ANOVA test is used for. It's again simple one. Is it? I'll wait just 1 minute. Can you please tell what will be the answer for this? So then that the null hypothesis for the one way ANOVA test is actually all population mean are equal. It's something will tell mu1 is equal to mu2 is equal to mu3. It's a status quo. Okay. So at least this is the answer. At least one population mean is different. It's a nothing. It's an alternate hypothesis. Okay. So this can't be the answer. The variance between the group is equal. It's an assumption. Okay. So it's some sort of assumptions, not the null hypothesis. And the sample mean follow a normal distribution. It's again assumption, not the null hypothesis. Okay. So one way ANOVA is used to test whether there are statistically significant differences between the means of three or more groups. If we have the two groups, so that we can go for the t-test, chi-square test, and all we can go. So if the group means are truly equal, the variation between the group with much larger than the variation between the group within and between the group it should be much larger now. If group mean differs, the between group variation will be the dominant. So that the null hypothesis will become all group means are equal and alternate should be at least one mean is different. In the case of alternative, there should be not like every mean should be different. If one mean came like some sort of unequal, it means we are going to reject the null hypothesis. What is the role of gradient in gradient descent? Just tell me what is the role of gradient in gradient descent? Gradient is something we are saying going to take the differentiation. It's a del L upon delta beta or del upon delta beta 1 or del upon delta beta 2. But what we are doing from that? We are going to determine the direction and magnitude of the parameter updates. Okay, so this is the correct answer. Actually, what we are doing the gradient to take the slope or differentiation to find out the optimized parameter. In that case, the loss will be minimized. In the case of linear regression, we'll do MSE should be minimized. In the case of logistic regression, that the our cross entropy should be minimized. So what we are doing, we are going to equate with the zero, then we can get the parameter that will be the optimized parameter. So They're going to give the determine the directions and magnitude of the parameter update. So this is the correct answer. So they represent the total error of the model? No. It's a just a differentiation. They're not going to tell, okay, what will happen, the error and all, but they can't give the error parameters. Why? The gradient is not the error, it's actually a slope. It's a slope. They help determine the final cost function value. No. How come? Just tell me. Final cost function, it will change upon the different parameters. Other factor, other parameters also. But the gradient will tell like how, which directions it can go and all, but will not tell the final cost function. So it's again can't go. Okay. They influence the number of iteration for the convergence. No, it's again it's the concept of learning rate. So in the gradient optimization that what we are doing, minimize the cost function. So the direction of the gradient tell us how to move parameter to increase the cost functions or maybe to minimize the loss. By moving into the opposite direction of the gradient, we reduce the cost. The magnitude of the gradient tell us how steep the slope is there. It's a controlling the size of the update. It's nothing to do with the error, nothing to do with the final cost function, nothing to do with the number of iteration. Number of iteration actually played by the learning rate. What are the following are key assumptions in one-way ANOVA? It's a simple one that we have seen already that the before. Population variances are equal across the group. Is it correct or not? Which of the following are the key assumptions in the ANOVA? First one is the independent. Group have equal sample size. That is not at all necessary. Okay. And observation variances are equal across the cross group. Population variance are equal across the group. No. And population should follow the nomination. Correct. So, one way ANOVA compare the across the multiple cross group, but valid only if assumptions hold independence of the observation, normality, and homogeneity of the variance. This with also. Okay. So, whenever we are going to solve any problem in the ANOVA or in the RCBD or T test and all, some key assumption that we need to follow it up. If that assumption is going to violate, that sometime will not get the whatever the answer we need or require. Okay, so now we'll come to the next question of what we have in the logistic regression. What is the relation between the log odd and linear predictor? Can you please tell? In the logistic regression, what is the relationship between the log odds and linear predictor? Log odds are proportional to the square of linear predictor. Whenever we are having linear, so it can't be the square. So we can eliminate these options. Is it? And the log odds are exponential function of the linear predictor. No, it's a sigmoid function. It's a form. It's a form of functions, but it can't be the exponential to the linear predictor. So it's again we have to eliminate it. Log odds are equal to the linear predictor. Yes, log odd are it's actually I told logistic regression is nothing else. It's a log function with the linear regression. So this is the answer. Log odds are logarithmic of the product of the linear product, and no, it can't be the randomly. It can't be the like randomly product of two variable. So log odds are equal to the linear predictor. So that is the correct answer. Well, if you see the LR is used for the binary classification. Instead of modeling the probability directly, we are using in the log odds that we call log it. Probability as a linear function of the predictor. Instead of I told like y is equal to mx plus c, that we are going with the log functions. So that is the log of p by 1 by p. It's something like this. Sigmoid function. It's a so the log odds are equal to the linear predictor. This is the log function. This is the linear function. So I think it's clear. Then what we have, which of the following is the valid stopping criteria in the gradient descent? We were having sigma L upon sigma beta naught, sigma L upon sigma beta 1. So, but something. Which of the following is the valid stopping criteria in the gradient descent? This is things saying zero, it's a stationary point, not the stopping criteria. It's a stationary, not the stopping criteria. So this can't be the answer. When the loss function start to increase, no, this could if loss function start to increase, what will happen? It's going to overshooting or overfitting. So this can't be the answer. When the change in the log function fall below a threshold value, whatever we put the threshold value, if it came below, it means it's a stopping criteria. Means after that there is no change will come. So it means this is the correct answer. When the number of features equal to the number of sample, that is not the case. That is the case of what we saw something we call that is a part of particular that the beforehand only. It's a not the stopping criteria. This is stopping criteria. Okay? Uncontrolled. That is totally related to that unrelated. Gradient descent is actually a iterative optimization algorithm. It stopped when no longer improve with the model significantly. When are we going to stop it? When there is no. So, and common stopping point includes maximum number of iteration reach or whatever the iteration we have fixed the number of iteration. Let's say 1,000, 1,500, 2,000. We kept it out so that if it is reached, so that's going to stop. Or change in the loss function is smaller than its tolerance. Okay, means something like we convert this criteria reach or change in the parameter value is very small. Let's say if we were doing the iterations and all, it went like this, and then it become like this. So there is no much of change is there. So that we can't do anything. So that is the starting point. So waiting for the gradient is exactly zero is impractical. It's a because of the numerical comparison. Monitoring the loss increase is useful early stopping, but not for the primary stopping rule. It's a useful, but not the primary stopping rule. What is the potential issue if the learning rate in gradient descent is too high? I think that we have discussed also. What is the potential issue? What is the challenges? For the case of when we are going to that the learning rate is become high, the model will converge too quickly. No, it's a overshoot or overfitting. The gradient will become zero too soon. No, it's again no, not correct. What will happen? Will become zero. Where? At a stationary point. The model parameter will overshoot the minimum and convergency may fail. Yes. Okay. The model will converge to a local minimum. No, it can't. It's a not related to the learning rate. So C is the correct answer. The model parameter will overshoot the minimum and convergence may fail. So in gradient descent, learning rate is actually control the size of the each step. If alpha is too large, convergence will become very slow. If alpha is too no too is the too small will be update may overshoot the minimum, causing the oscillation around the minimum or divergence will become. Now we'll come to the next question. What we have in randomized control block design, if there is significant interaction between the block and treatment factor, what does this imply? If you see that our assumptions, we didn't ask for like to there should be any interaction, is it? That we didn't ask for any interactions and all. So that assumptions of the RCBTs are violated. That the treatment effect is consistent across all blocks. It's a effect. It's a afterward we can check it out. So this can't be the answer. The blocking factor had no effect on the response variable. How come you can say that? It's there might be no difference with once we do the testing. So this absolutely is correct. This can't be. The treatment effect varies depending on the blocks. Yeah, it can be. It can vary. It cannot vary. So means whenever there is a interaction effect is there, so we'll say they are going to violate the RCBD assumptions. So this is the D is the correct option. Okay. What does the term convex function imply in the context of gradient descent optimization? I think that one function we have told in the starting. What will happen? What does the convex function imply in the context of gradient descent optimization? In that case, function has a single global minima or maximum value. A convex function if the line segment between the two any point function lies above or on the curve. Convex function will show like in optimization, convex has a important properties like convex function has only one global minimum. It's something like this will tell below or something. There are no other local minima. It should be not like this. Okay, only one global minima should be there. So this can't be the option. This makes convex component much easier to optimize. So it means they'll be having single global and local minima. This is the correct answer. There is single local minima but multiple global minima. No. So there are multiple local minima, single global minima. No. They'll be having only one. Only one. The function has the both multiple local and global maxima. No. So when the convex function, they're going to tell only single global minima or local minima only. So now we'll come to that the last two question. When the cross entropy in the classical task loss function becomes smaller when The predicted probability of the correct class increase. Yeah, the predicted probability of the correct class should increase. Predicted probability of the incorrect class will increase means it's going to be a when it's going to increase the loss actually. Why? Because not not classifying correctly. It means loss is more. So this can't be the answer. The predicted probability and are equally distributed across the classes. That is not the case. This is unrelated. Model or fit training data. It's again, it can't. So it means cross entropy loss measure the distance between the true distribution label and predicted. For the one hot and cold classification, it's become like this. So loss decreases, model assign higher probability to the correct class, not the incorrect class. Which is the following assumption of the ANOVA? Homogeneity? Yes. Normality? Yes. Independence? Yes. Not at all. Is it? So, that's all for today. If any doubt is there, please ask. Hello?
So any doubt in next class, you will ask, sir.
Yeah, sure. So, for the session today, it's okay or bit of complicated?
Okay, sir, some doubts are clear. Okay, we can able to understand the day's process.
Okay. Okay. Thank you. Thank you so much.
Thank you so much, sir.